First group is station operation and setup. What's the purpose of a notch filter found on many HF transceivers? Let's take a look at a graphic here and see how the notch filter works. The purpose is to reduce interference from carriers in the receiver passband. And if you look here you can see a passband of a receiver. And here's the signal you want right here in the center of that passband. But also within that center, there's another signal there that you don't want, and it's interfering with you hearing the other one. It's called QRM, which is the Q code for man-made noise. And so there are several ways you can get rid of that. This particular question deals with using a notch filter. And if you have a notch filter control in your receiver, you can put the notch right over that other carrier, that QRM carrier, and notch it right out of your intermediate frequency processing. So that's the purpose of the notch filter, is to reduce interference from carriers in the receiver passband. What's one advantage of selecting the opposite or reverse sideband when receiving CW signals on a typical HF transceiver? The CW, some transceivers give the option of going CW or CW reverse, and what it does is just put it on the other side of the intermediate frequency so that you may be able to use that to reduce or eliminate interference from other signals. What's normally meant by operating a transceiver in split mode? In split mode, the transceiver is set to different transmit and receive frequencies. Now, the way they're using it here, we don't normally talk about split mode when we're talking about repeaters, but of course that is what we're doing, isn't it? Because we have the receive frequency and then we have the offset for the transmit frequency when we're transmitting to a repeater. When we talk about split mode, we're normally talking about high frequency. And although the principle is exactly the same, the receiver is set so that it transmits on a different frequency than it receives. And the way you normally do that, if you have two VFOs, you'll set one up to be your transmit VFO, the other one to be the receive VFO, and it switches back and forth. And in some transceivers, that can even be in two different bands. So you can have a really wide divergence in your transmit-receive frequencies if your antenna will accommodate that. What reading on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? Okay, so we're talking about a vacuum tube RF power amplifier. This is back in the good old days when you could heat your ham shack with your radio. On the plate current meter, you'll have, as you tune the amplifier, as you bring the circuits into resonance, the current will be high, and at resonance, it will drop back down. There will be a definite dip there, and then if you go past that resonant point, it will go back up again. So the correct resonance point in the RF power amplifier will be in the dip. There will be a pronounced dip when the amplifier is correctly tuned. What's the purpose of using automatic level control with an RF power amplifier? The purpose is to reduce distortion due to excessive drive. And we've seen these pictures before of the two-tone test for single sideband. And basically, if you have a normal signal with normal drive, you have an envelope on your signal that looks like this. If you are driving it too hard, then you get distortion, and that causes the flat topping that we've seen in some of the other questions. Also causes it to pinch more in here, and you get that kind of distortion that causes audio distortion and so on in your transmitted signal. The automatic level control is helps prevent that. What type of device is often used to enable matching the transmitter output of an impedance to an impedance other than 50 ohms? We've talked about the importance of matching your matching everything in your from your transmitter all the way to your antenna, and they're asking what kind of device you do this with. The device is an antenna coupler, and here are a couple of examples of antenna couplers. This is a manually tuned coupler here. Here you can see the knobs that you use to tune it. Here you have a large capacitor. Here you have a large variable, this is a variable capacitor, a large variable inductor. And here you have another large variable capacitor. And these are manually tuned for the best indication of match for your antenna system. This picture over here is an automatic antenna tuner. And here it's all done by a computer watching the signals and switching the inductances and capacitances in and out of the circuit until it gets the best match. And usually these will also memorize frequencies so that once you have tuned up on that frequency, it can go back to the correct combination of inductances and capacitances just in a fraction of a second when you tune up again on that frequency. What condition can lead to permanent damage when using a solid-state RF power amplifier? Excessive drive power will cause it to overheat and will damage the power amplifier, excessive drive power. What's the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? Okay, now you'll remember we did the plate tuning control, or we went for the dip on that. Once we achieve that dip, tuning the plate resonance, then we go with the coupling control. We go for maximum power output without exceeding the maximum allowable plate current. So we tune to the dip, and then with our coupling control, we will couple the antenna to it to whatever allowable power plate current is allowable for that amplifier. So we may dip down to here, and then when we put the coupling back in, it will come up to here. Now that doesn't change the resonance of the dip. The resonance of the dip will still be down here where it belongs. But we just then bring the amount of power we're taking out of the tube up here to wherever our maximum allowable is, assuming we want to run maximum power. But that's what you would normally do. Why is a time delay sometimes included in the transmitter keying circuit? It's to allow time for the transmit-receive changeover operations to complete properly before RF output is allowed. Sometimes if you have a transceiver and maybe a power amplifier hooked up to it and some other things going on, it takes a little time for all of that to drop into place, and a delay in the transmitter keying circuit can allow all of that to happen before RF is applied to the circuits. That way you're not switching under power, which could cause damage to relays and that sort of thing. What's the purpose of an electronic keyer? Electronic keyer. Now most of the modern transceivers, HF transceivers, have the keyer built into them. But here's an example of a standalone keyer. This is a Heathkit. It was a very popular kit from Heathkit when they were out. In fact, I built one of them. And it automatically generates strings of dots and dashes for CW operation. In this particular one, if you push on one of these paddles, it does a string of dots. And if you push on the other paddle, it does a string of dashes. And if you squeeze the two of them, it does a da-da, 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 da-da for as long as you can hold on to it. Some hams like that style with the two paddles. Some hate that style and like it with a single paddle. You push it one direction, you get dots. You push it the other direction, you get dashes. But anyway, it's for the automatic generation of strings of dots and dashes for CW operation. Which of the following is used for the IF shift control on a receiver? Now, here we're using this similar to the way we used the notch filter before, but what we're doing, here we have the desired signal again. Here we have our interfering signal again. This time, we didn't have a notch available, but we were able to shift our IF window far enough over so that it kept the desired signal in place inside the response curve, and shifted the response curve to where the undesired signal was no longer in the curve. So in that way we got rid of that undesired frequency close to our desired receive frequency. So the shift control, IF shift control. Which of the following is a common use for the dual VFO feature on a transceiver? This is what we talked about back there with the split operation to permit ease of monitoring the transmit and receive frequencies when they are not the same. So again, you can, what you normally do is set it up for, the VFOs are usually named A and B, and you just set it up for an A-B split. And just depending on how you set switches, you can listen on either of the frequencies, or you can transmit in one and receive on the other, and so on. That's the dual VFO feature on a transceiver. What's one reason to use the attenuator function that is present on many HF transceivers? An attenuator cuts down signal strength, reduces signal strength, and we do that to reduce signal overload due to strong incoming signals. If we're getting too strong a signal into our receiver, we turn on the attenuator, and that helps to cut that down to where the receiver can handle it and process the signal better. How should the receiver audio input be adjusted when transmitting PSK31 data signals? The test answer is so that the transceiver ALC does not activate. Now, I'm not sure exactly what that means in terms of a real-world transmitter. So if you get into PSK31 or any other data modes, be sure to do what the manual says, both the manual for your transceiver and the manual for your PSK31 system, and do what it says. But for the schoolhouse answer here, for the test, the correct answer is so that the receiver ALC system does not activate. And that might mean that it's set low enough that you don't even get an indication here on the ALC scale on the meter. I'm not sure exactly what that answer means. All I know is that's the correct one for the test.